Variance test. Introduction. A variance test is a statistical method used to compare the variability, spread or dispersion, of data within or between groups. It helps determine whether the variances of two or more populations are significantly different from each other. Commonly used tests include the F-test, for comparing two variances, and Levene's test, or Bartlett's test, for multiple groups. Variance tests are important because many statistical methods, like ANOVA or t-tests, assume equal variances across groups. Testing for variance helps validate those assumptions and ensures the accuracy of further analysis. Welcome, everyone! Before we begin, let me give you a quick overview of what we'll be covering in today's session. By the end of this session, you'll walk away with practical, hands-on knowledge that you can apply in your own work, especially when analyzing variability in processes. Here's what we're going to cover. 1. Variance. We'll start by understanding how to analyze the variance of a single dataset. This includes situations where you're trying to determine if the variation in your data is acceptable or not. 2. Variance. Next, we'll move on to comparing the variances between two datasets. This is crucial when you're assessing consistency between two processes or groups. Test for equal variances. Finally, we'll look at formal tests that help us decide whether variances across groups are equal. This is especially important before applying many parametric tests like ANOVA or the two-sample t-test, which assume equal variances. So, by the end of this session, you'll not only understand what variance means in practical terms, you'll also know how to test it and use those results to make better data-driven decisions. In this section, we'll explore how variation in a continuous outcome, y, can be analyzed across different groups or categories of a discrete input, x. When we have a continuous y, such as handling time, production output, or cycle time, and a discrete x, like department, shift, or team, our goal is to understand: does the grouping factor x cause meaningful variation in y? This helps us determine if certain categories of x are influencing the response variable significantly. And that's critical in process, improvement, and root cause analysis. To analyze this relationship, we rely on variation testing, and here are the key types. 1. Variance test. Use this when you want to compare the variance or standard deviation of your sample to a known or expected standard. For example, is the variation in delivery time higher than the acceptable threshold? 2. Variance test. Use this when you want to compare the variance or standard deviation between two independent samples. Example: comparing variability in response time between two different teams. Test for equal variances. Before applying ANOVA or similar statistical methods, it's important to check whether group variances are equal. This test tells us whether it's safe to proceed with parametric tests that assume homogeneity of variance. We often use tools like ANOVA for normal data or Kruskal-Wallis when the data doesn't follow a normal distribution. In summary, understanding how variation behaves across discrete groups helps us pinpoint inconsistency, improve process control, and make better decisions based on data. Let's talk about the 1. Variance test, which is used when we want to determine if the variance or standard deviation of a sample is equal to a known or expected value. This is important when setting baseline performance, evaluating consistency, or validating if a process is in control from a variation perspective. When to use. You apply this test when comparing a sample's variance or standard deviation against a fixed or standard value. It's especially useful for baseline analysis. For instance, when launching a Six Sigma project, you can use this to determine the natural variation in your process before improvements begin. Null and alternate hypotheses. If checking variance, H0, variance equals the standard. H1. Variance is not equal to the standard. If checking standard deviation, H0. Standard deviation equals the standard. H1. Standard deviation is different from the standard. This helps assess whether your current process variability aligns with expectations or if it's drifting. Examples. Suppose you have a batch of Wagon R cars, and you want to verify if the mileage variation aligns with the company standard. This test will help. If you have continuous data like handling time, this test helps you understand whether the variability in performance is within an acceptable range. You can also use the confidence interval it provides to set targets or define acceptable performance limits. In summary, the one-variance test is not about comparing means, but rather how spread out your data is. A critical metric when trying to reduce process variation and improve consistency. In this slide, we look at how to perform and interpret a one-variance test using Minitab. Path in Minitab. First, understand that Minitab offers two methods. Chi-square method, best for normally distributed data. Bonnett's method, more robust and suitable even when the data is not normally distributed. In this example, we are testing whether the standard deviation, sigma, is equal to 0.45. How to study the result? Focus on the p-value. If the p-value is less than 0.05, we reject the null hypothesis. That means the population variance is significantly different from the specified value. If the p-value is greater than 0.05, we fail to reject the null, meaning the population variance is not statistically different from the target. In the example shown, the chi-square test gives a p-value of 0.000, which is clearly less than 0.05. So, we reject H0 and conclude that the population variance is not equal to 0.45. Also note, if your data is non-normal, you should rely on Bonnett's method for a more reliable result. Key tip: always check the normality of your data first before deciding which method to use. And if in doubt, use Bonnett. It's more robust for real-world data. 2. Variance. In this section, we'll discuss the two-variance test, which is used to determine if two population variances are significantly different from each other. When to use this test? You use a two-variance test when your goal is to compare the variability, or standard deviation, between two different samples. For example, let's say you have handling time data from two different call center teams, and you want to know whether the spread or consistency of handling time is different across the teams. This test helps you evaluate that. Hypotheses. Null hypothesis, H0. There is no difference in the variance or standard deviation between the two groups. Alternate hypothesis, H1. There is a difference in variance or standard deviation between the two groups. So if you reject the null hypothesis, you conclude that the variability differs between the two populations. Examples. You want to compare whether the standard deviation in mileage of two batches of Wagon R cars is different, or you want to check if the handling time of two types of calls varies significantly. Maybe one type is more consistent while the other is more variable. Why is this important? Knowing whether variances differ helps determine if you can proceed with other tests, like the t-test, assuming equal variances, or if adjustments are needed. It's a crucial step in the data validation process during your Six Sigma analysis. Let's next look at how to perform this in software, like Minitab or Excel. Now that we've run the two-variance test, let's look at how to interpret the result using the output shown on the slide. Understanding the output. We're comparing the variance in handling time between the morning and evening shifts. The null hypothesis here is that both variances are equal, while the alternative hypothesis states that the variances are not equal. What the p-value tells us. The p-value from the F-test is 0.487, which is greater than 0.05. This means we fail to reject the null hypothesis, and we conclude that there is no significant difference in the variance of handling time between the two shifts. In simple terms, both shifts show similar variability in their performance. Normality check matters. Depending on whether your data is normally distributed or not, you choose the appropriate test. If the data is normal, you accept the F-test result. If the data is not normal, refer to Levene's test, also shown, which is more robust for non-normal data. In this case, Levene's p-value is also greater than 0.05, reinforcing the conclusion. Summary. So, in this example, we are confident that both shifts have similar variance, and you can move forward using pooled variance if needed in future analysis like t-tests. Today, we're going to discuss the test of equal variance, a crucial statistical method used when we want to determine if the variances, or standard deviations, of two or more samples are approximately the same. This test helps us understand whether differences we see in data spread are significant or just due to random variation. There are two key hypotheses involved. Null hypothesis, HO, the variance of the samples is approximately equal. Alternative hypothesis, HA, the variance of the samples is significantly different from each other. This test is essential when comparing two or more groups, especially when you're about to run other statistical tests that assume equal variance, like t-tests or ANOVA. Let's break this down. When to use. You use this test when you're comparing the variability in different groups. For example, when comparing the standard deviation or variance of more than two samples to understand if they differ significantly. Null and alternate hypotheses. The null hypothesis assumes that all sample variances are equal. The alternate hypothesis suggests that at least one sample has a different variance. Common tests for this include Bartlett's test, F-test, and Levene's test, which are available in tools like Minitab. Examples. You might compare the variance of mileage across two batches of a vehicle model, say Wagon R, to see if there's inconsistency in production. Or you may compare handling time variances for two different call types in a call center. In summary, the test of equal variance is a foundational step to ensure the validity of your statistical comparisons. Let's take a deeper dive into how we perform the test for equal variance, particularly using Minitab. When performing this test, it's important to first determine whether your data is normally distributed or non-normal, because that determines which test results we should rely on. If your data is normal, when comparing two samples, look at the F-test results. When comparing more than two samples, rely on the Bartlett test. If your data is non-normal, regardless of the number of samples, use Levene's test, which is more robust against deviations from normality. Now, when using Minitab, you'll get results from both the Bartlett F-test and Levene's test simultaneously. So, how do we interpret them? If your data is normally distributed, you focus on the p-value of either the F-test or Bartlett test, depending on how many samples you are comparing. If your data is not normally distributed, then you rely on the p-value of Levene's test. As you can see in the image, under the stat greater than ANOVA, greater than test for equal variances path, in Minitab, you can access this test directly. This makes the analysis efficient and ensures that you're using the right statistical method depending on your data type and sample size. Remember, a small p-value, typically less than 0.05, indicates that the variances are significantly different. A large p-value suggests that the variances are approximately equal, and you can proceed assuming equal variance. This slide shows a practical output of the test for equal variance from Minitab. The plot here represents the standard deviation confidence intervals for different team leaders, which helps visualize the spread of the data across these groups. On the right side, you'll notice two statistical test results. Bartlett's test, used when the data is normally distributed. Levene's test, used when the data is not normally distributed. Let's break down how to interpret this. Step 1. Check for normality. Before looking at the p-values, always check if your data is normal or not using a normality test, like Anderson-Darling or Shapiro-Wilk. Step 2. Choose the correct test. If your data is normal, refer to the Bartlett's test p-value. If your data is non-normal, refer to the Levene's test p-value. Step 3. Interpret the p-value. A p-value less than 0.05 indicates a significant difference in variances across groups. A p-value greater than 0.05 suggests that the variances are not significantly different. In the chart, the Bartlett's test p-value is 0.396, which is well above 0.05, so we fail to reject the null hypothesis, indicating variances are likely equal if the data is normal. The Levene's test p-value is 0.023, which is below 0.05, suggesting significant differences in variance if the data is non-normal. So, depending on your data's distribution, you'll accept either the Bartlett or Levene result, but not both. This is why knowing your data's normality is critical before deciding. This slide provides a comparison of three important statistical tests used to analyze variation in data, whether you are working with normal or non-normal distributions. It's crucial when assessing standard deviations or variances, especially in continuous data analysis. Let's walk through each of the three tests. 1. I-variance, when to use. When comparing a single sample's variance or standard deviation to a known baseline or standard. It's useful when validating a baseline or checking if a current process aligns with a set target. Hypotheses. If checking variance, ho, variance equals the standard. I-hey, variance is not equal. If checking standard deviation, ho, study dev equals the standard. AA, study dev is not equal. Example. Comparing mileage variation of a batch of wagon R to a defined baseline, or using historical standard deviation to understand consistency over time. Remarks. If data is normal, use the chi-square test. If data is non-normal, use Bonnett's test. Second. 2. Variance. When to use. When comparing variance or standard deviation between two samples. Hypotheses. Ho. Variance or standard deviation. Developer of both samples are equal. Ha, they are not equal. Example, comparing standard deviation of mileage between two different wagon R batches, or evaluating handling time consistency across two types of calls. Remarks, if normal, use F-test. If non-normal, use Bonnett's test. Third, test for equal variance when to use. To compare variance across two or more samples. Hypotheses. Ho, all variances are equal. Ha, at least one variance is different. Example, comparing variance of mileage across more than two batches of wagon R, or comparing handling time variation among multiple managers. Remarks, if normal data and two samples, use F-test, otherwise use Bartlett. If non-normal or more than two samples, use Levene's test. Final note, bottom of slide. Make sure these tests are only used when Y is continuous, like mileage, time, weight. X is discrete, like category, manager name, batch, number. These tests help validate consistency and identify if your process variability is under control or needs attention, which is critical for any data-driven improvement.